I'm Matthew Buckner. I'm from UNC Chapel Hill. I work here at the Laboratory for Experimental Nuclear Astrophysics. And the title of my talk is Thermonuclear Reaction Rate for Oxygen 17, P gamma, Fluorine 18. So I'd like to provide a brief summary of this talk before I get started. Just give you a little bit of motivation, a little bit of background about what I'm going to talk about today. The phenomenon of interest, because I am at heart an astrophysicist as well as a nuclear physicist, is classical novae. I'll then talk about this and then talk about the actual nuclear reaction I care about, O17 P gamma, and then discuss direct capture, which is a subset of the nuclear reactions that are occurring during this particular reaction. I'll then describe some of the previous measurements that have been made for this reaction, and then some of my preliminary calculations that I performed to really ground the experiment and set myself up for really pretty much making a roadmap for myself how I was going to go through this experiment. I'll then provide some of the projections I arrived at, and then show you the lay of the land where I am right now, where I see things going. Hopefully I'll provide you all with a narrative for how I got to where I am right now in this experiment, where I see it going, and yeah, let's continue. So classical novae. When you start talking about classical novae, you care about a unique type of star called a white dwarf. This is a compact stellar remnant that's left over after a much more massive star, perhaps 9 to 10 solar masses, has proceeded through its evolutionary life cycle, ended its life, and expelled all of its envelope material and exposed this electron degenerate core that we refer to as a white dwarf star. Astrophysicists will often show you a figure like this. This is usually a figure that's describing a collection of stars, like a globular cluster. And all it's showing you is the evolutionary path that each of the component stars in this globular cluster are actually on at a particular time. So the stars that lie along here might be more similar to our sun, and they're burning hydrogen to helium in their cores. And we refer to this as the main sequence. And then you have this turn-off point where the next stages of stellar evolution are occurring. You then proceed down, and here are very dim, barely visible white dwarf stars on this temperature versus luminosity scale here. So a classical nova is a thermonuclear explosion that occurs on the surfaces of these compact stellar remnants. This is an example of a remnant from this event occurred in the early 1900s, this particular nova event. And this is the ionization remnants that's left behind from that event. Only supernova and gamma ray bursts exceed classical nova in energy, but the interesting thing here is that when you study these phenomena, these are recurring events, so you'll continually be able to keep on, hopefully, observing them in nature frequently. And they're an interesting melding of both chemistry, physics, and computer science. A lot goes into the analysis of these stellar events. So here is an artist's mock-up of what a classical nova might look like. You have a main sequence companion in a binary star system, and then you have your compact stellar remnant, the white dwarf. And it's accreting matter from its companion by Roche-Lobe overflow. Accretion disk will occur, usually, and you get layers upon layers of accreted hydrogen-rich matter on the surface of this degenerate stellar remnant. And this matter is heated by compression and by nuclear reactions that are occurring, and it becomes electron degenerate on its underbelly there. And you'll eventually reach a point where you're just increasing the temperature so dramatically, and because it's electron degenerate, pressure no longer depends on temperature, so you can get this thermonuclear runaway that occurs. You get very intense nucleosynthesis occurring over the span of perhaps only a few hundred seconds. And this has interesting implications for what's actually produced. I'll get to that in a second. And as I said, these are recurring, so this system is not disrupted by this event. So again, it'll start to cool and then eventually start accreting again after a nova event. And we estimate there's about 35 plus or minus 11 per year in the galaxy. So the ejecta from the actual nova event can kind of relay very interesting information about the underlying white dwarf, about the actual thermonuclear runaway that's occurred, peak temperatures, expansion time. You can use this information to constrain stellar models. You can constrain burning models and gain lots of really valuable information. There's going to be some amount of mixing between the core matter and the accreted matter here. And there's significant efforts underway to understand this better and the mechanisms driving this, because they'll ultimately affect abundances that can then be observed within our galaxy. shear mixing, elemental diffusion. These are just some examples of what might be driving mixing between accreted matter and core matter. So, as some of you may have guessed, when I'm talking about nucleosynthesis, I'm talking about CNO cycles, okay? And specifically for my particular reaction, I care about the hot CNO2 cycle, where I'm just starting off at O16, proceeding to fluorine-17 by a proton capture, then a positron emission and another proton capture, then an alpha emission, a positron emission, and another proton capture back to O16. Because we're dealing with such a very short time scale here, on the order of just a few hundred seconds, the CNO never quite reaches equilibrium. In a star perhaps a little bit more massive than our sun that's undergoing just normal CNO processing, you'll eventually reach a point of equilibrium where you're not really destroying these catalysts that are driving the fusion here. Basically, you don't lose anything, you don't gain anything. But here, because the time scale is so short, you actually get the opportunity to create a bunch of really exotic things like oxygen 17. We produce a whole bunch of beta unstable nuclei. You can see all these beta decays occurring here. And they all convect to the surface initially. And they are actually, as they decay, they're driving the expulsion of matter during this explosive event. So, again, these are isolated events. They are reoccurring. They're perhaps producing about a 3,000th of the galactic dust and gas that's out there. But they're very significant sources of O17 in particular, also carbon-13 and nitrogen-15. Oxygen-17, as some of you may know, is the rarest oxygen isotope. In our solar system, it accounts for only about 0.038%. And just to put that in perspective, for my targets, a sample of oxygen-17 enriched water runs you about $2,500. That's just for 1 gram. So in classical novae are thought to be perhaps the only, if not the major source of this O17. So all of my samples, my oxygen-17 enriched water samples, that O17 was very likely produced during one of these events. So how could we perhaps observe one of these events from an astronomical perspective, let alone within the laboratory? So 511 keV radiation is produced when the positron annihilates with an electron. The problem with that, though, is you basically have to point your detection equipment, let's say the integral satellite, at the exact location in the sky, because you would observe these 511 keV gammas before you actually observe the nova in optical frequencies. So you have to get very lucky with that. So our thought is to try to just learn a lot about the fluorine-18 content of these events by actually directly studying oxygen-17 P gamma in the laboratory. So here's a nice picture of integral. Why is fluorine-18 in particular all that important? Well, as I said, you have a bunch of nitrogen-13 produced, a bunch of fluorine-18 produced. The problem is because of the half-life of both, nitrogen-13 is going to produce its positron. Positron is going to annihilate. You're going to get your 511s before the envelope actually becomes opaque. And then the fluorine-18 is going to beta decay. And when it does, you're going to produce a whole bunch of 511s after the envelopes become transparent. So what you're probably going to see if you were to actually observe 511s with integral immediately before observing the nova and optical frequencies, you'd be seeing the 511s from fluorine-18. So again, you can learn a lot about the fluorine-18 content if you can make these observations, or if you can go ahead and measure the thermonuclear reaction rates experimentally. So here's that CNO cycle again. We're going to focus in here on O17, capturing a proton, the fluorine-18. There are, of course, a broad history of thermonuclear reaction studies for this reaction, but rates still remain relatively uncertain. So basically the goal here is to improve upon previous measurements, improve these uncertainties, study this directly, and try to draw some conclusions about oxygen-17 and fluorine-18, the fluorine-18 content produced by novae, the oxygen-17 abundances we observe in our galaxy in meteorite samples, pre-solar grains, and try to understand explosive hydrogen burning all the more better. So at LENA, we perform our reaction rate studies in a very unique way compared to perhaps some other groups. We try to ground our reaction rates in a statistically meaningful way. We try to make sure our rates are physically motivated when we perform these calculations. We assign probability density functions to every variable that's entering into these calculations and perform rigorous Monte Carlo analysis and some of the input to these calculations include experimental resonance strengths and astrophysical S factors and partial widths. And the output then, this is not a fit here, but this is the black line is the actual probability density function that we're positing we were going to produce, and the red here is the actual Monte Carlo output from our calculations. So this is what I'm working up towards, is actually being able to produce some of these rate figures here and start drawing some conclusions based on these. So this is just a preliminary input with some previous established rates. So if I'm going to start to define an experiment, I need an experimental window to study. Okay, so how do I do that? In astrophysics, we have a well-defined concept of the Gamow window, which is just a temperature regime for a reaction, for nucleosynthesis to occur within a certain stellar environment. For classical nova, that temperature regime happens to be about 100 to 400 megakelvin. We can then calculate out this Gamow peak concept, which is just the product of the Gamow factor and the Maxwell-Boltzmann factor. And that can then give us an idea of what proton energies we're actually going to need in the laboratory to probe this region. I want you to focus in on how low this energy is. This is 103 keV, and that's going to be important in a few other slides, because I'm going to show you how we're going to try to step further and further, lower and lower in energy than perhaps some previous groups have in the past. So again, here's the Gamow window. I mentioned direct capture before. This slide really shows you why I think direct capture is important here, and why previous groups have also made the argument that direct capture is important within this energy regime. These are fractional contributions to the overall thermonuclear reaction rate as of right now, before I've made any additional changes to this. And direct capture is dominating over a sharp resonance at about 183 keV here. This is the fluorine-18 level diagram, and this is this region, this Gamow window region within the level, just to give you some perspective within the level diagram, what that corresponds to. So what exactly is direct capture? It's a little bit different from actually forming a compound nucleus. A compound nucleus is not actually formed when the proton strikes our nucleus of interest here. The proton is directly captured from the scattering state to the bound state, but we basically neglect the nuclear interior because this is mostly an exterior reaction. No compound nucleus is formed, but we do get a gamma cascade produced, and that's well-defined and well-documented. So I have some blueprint to start looking for in my data for whether or not I've observed this particular type of phenomenon. And here's the lay of the land as of right now, before I add my own contribution to this. You can see there's several decades worth of study here, some very recent, some from quite a while ago. I would like you to just focus on two important things here. The energy, again, none of these are quite getting down to that lower limit there, the 103 keV. Also the beam current, okay? So lower current is going to result in you not being able to produce as high a reaction yield. So it's going to require more charge to target. It's going to require more experimentation time. It's going to require more targets ultimately. So based on the equipment I have available at LENA, I want to start providing a good sense of what my, with what I have. Can I actually perform this experiment better at lower energies more quickly? And I would like to argue that my answer is yes. I also wanted to point out that these experiments are all done in kind of different, interesting ways. Some are prompt gamma ray detection, some are by actually activation. So you create fluorine-18 during this process, and then it beta decays, so you're studying the activation instead of the actual gamma cascade. And then also there was one experiment done at Triumph in inverse kinematics. And then these are the results of that experiment. This is the astrophysical S factor on the y-axis and the center mass energy on the x-axis. We have a slight additional complication here because we have contributions from broad resonances in the low energy region that we care about. So this dotted line here would represent the direct capture contribution, and then this dotted line here, the black one, is the contribution from broad resonances, and the sum of these gives you what you would actually observe before actually trying to deconvolute the direct capture component of the actual reaction. So this is the lay of the land up to this point, getting lower and lower in energy, but then basically stopping at about 200 keV, and this guy has some pretty high uncertainty bars there. So we'd like to do better, get lower, improve the rates, and get a better sense of what's going on here. Just for those unfamiliar with what the S factor means, it's a cross-section We divide energy out. We divide the Gamow factor out here, or we take the Gamow factor out here, and then this is the astrophysical S factor. So, I wanted to just mention, this blue line here is my initial calculation at my initial starting point here. It's not a fit. These are actual model calculations, and this was a very important stepping stone because, as I'll get to in a few slides, this code, TEDCA, gives you is a nuclear cross-section calculator. You can define potentials. I used a zero scattering potential to start off. You can then gather spectroscopic factors from the literature to start defining what you expect the cross-section or S factor to look like. And what's important for me in these initial calculations, not so much the overall result of the cross-section result here, but I can extract out my branching ratios and then feed these to a J-4 simulation to start estimating very important values like my count rates, the amount of charge I'm going to need, ultimately the number of targets I'd want to actually put university resources into producing, because, as I said, O17 is very expensive, so I need to have a good sense of where I'm going with the experiment. So I'll start to get into some of the interesting tools that we have available to us at LENA to perform an experiment like this. So we use a gamma-gamma coincidence detector configuration. Basically, our target is right here. It's got water cooling right behind it at the end of the beam line. This is a copper collimator, and the beam is traveling this way down the beam line. In a very close running geometry, we have a high purity germanium detector right up against the back of this target chamber. Surrounding this is a sodium iodide annulus. And basically, the idea here is that we have set energy and timing gates in our electronics to isolate out the actual gamma cascade. So we have a whole bunch of room background. We have a whole bunch of muon events. We can isolate the actual reaction we care about by making sure that we're looking for events that correspond to both detectors simultaneously. So you'll get an event here. You'll get gammas produced that go to the germanium, go to the sodium iodide. You can then gate in an intelligent way. This is an example of one of our 2D gates, 2D trapezoidal gate. And you can see the reduction here. This is just the high purity germanium spectrum. This is the spectrum produced after these coincident cuts have been made. And this is about a factor of 100 drop in background. So this is a very useful way to boost signal to noise initially. So it's just one of many steps we have to take as we go lower and lower in energy. We're running into the Coulomb barrier, and our cross-section is dropping dramatically. So again, there's been a whole lot of study of this reaction at higher energies. We're focusing lower and lower, so signal to noise, boosting that, very important. So the next piece of the puzzle, as you start to try to calculate out where things are going to go, what you're going to need to do, you need to know the efficiencies of your detector. And this is done in a very well-known way at LENA. We basically set up a yield equation, and we start providing sources and well-known nuclear reactions. We can calculate out the efficiencies of our detector using this and project out using J-ONT2 what we expect things to look like when we are actually going to be looking at particular efficiencies for particular portions of the decay from the gamma cascade produced by direct capture. So that's one portion of the puzzle. But we also have a sodium iodide annulus we have to take into account. So that gets more complicated. We need total efficiencies there. And we need to take into account the fact that there's going to be efficiencies that are going to be modified due to the fact that we're using coincidence technique. And that's where we rely on J-ONT. And this is just to show you that our data and Monte Carlo agree relatively well. Any deviation you see here is just a resolution effect that can be changed as we go through the experiment and have a better sense of what our germanium resolution is for each set of data. We can then change the resolution on the Monte Carlo. We can add in more backgrounds if we have to. But this is just to give you some sense of how well we trust our Monte Carlo's agreement with our data. And right now, this figure stands at about they agree within 4%. So we can then calculate out this value here, which is actually way more complicated. We call it the F gamma value, the coincidence correction factor. This is accommodating for the efficiency due to the total efficiencies of the sodium iodide and branching ratios of the gamma cascade that's being produced. And this is basically just the product of those branching ratios and efficiencies all wrapped up in here. And because we trust our Monte Carlo very well, we can start to set up on post-processing all the gating we're going to perform to basically reproduce exactly what we would expect to see from performing the experiment and calculate out these efficiencies. So this is just a good starting point for figuring out all these important things like count rate, basically, before you actually perform the experiment. So then this is just efficiencies for direct capture plus those broad resonances and efficiencies for just the direct capture portion. So again, here's the energy region I'm going to focus in on. I'm just going to start here at higher energies at about 325 keV lab, work my way down to about 125 keV lab. We have two accelerators at LENA, and they're both well suited for separate energy regimes. I'll get into a diagram of LENA in a few slides, but I'm basically going to break the experiment. Well, I've broken the experiment into two phases: a high energy phase, high in quotation marks, and a lower energy phase. I've written a Monte Carlo code that solves for the amount of charge I expect at each energy point and the number of targets I'll have to produce, and thus how much university resources I'll require. Move on a little bit. This is LENA. We have an ECR ion source, 50 to 215 keV beam. We have a JN Van de Graaff, this big purple accelerator here, 200 to 1 MeV beam. Our ECR ion source can produce 1.5 milliamp at target. So that is a larger amount of current than previous experiments have used to probe this particular reaction. And that gives us a bit of a leg up because we can boost our reaction yield significantly as we go to lower and lower energies and probe much more difficult energy regions. So then here's just some count rate estimates based on the calculations and all of the input that I've shown you through the past few slides. That's not perhaps quite as interesting as just how much charge I'm going to need. So for the first 5 data points at higher energy, just 25 Coulomb would be sufficient, but at lower energy, I'm going to need almost 450 Coulomb. So that's quite a jump up. You can kind of get a sense from that how dramatically my cross-section is dropping. I'm going to need a ton of charge at low energies. We analyze our targets constantly during an experiment to make sure that the intense beam is not degrading the target surface significantly. We use our JN for that, and we use well-known resonances. So the 519 keV resonance in 017 gamma is well-known. So we can check its strength continually. This is an example of oxygen 18 gamma with the 151 keV resonance. That's the kind of profile we produce. So we can check the yield, we can check the resonance strength kind of on the fly as we're going with the JN. It's a great probing tool. And right now, I've only put up to about 30 Coulomb on a single target right now, but I have a handful of targets already. But my estimate is I could probably exceed 30 Coulomb per target with the oxygen 17 targets I have. So before I started making targets, I had this estimate that I needed about 5 at high energy and 16 at lower energies for the ECR. And then here is my target fabrication process. So we acid etch our tantalum backings. These are ultra-pure tantalum substrates. We then resistively heat in a vacuum to remove any other surface contaminants. And then this is an anodization chamber I designed and had machined at the UNC shop. And then you produce this nice oxygen 17 target through an anodization process. So where am I right now? The first 5 data points have been collected, and the analysis is underway currently. As soon as I get back to North Carolina, I'm going to start 24-hour, 24/7 runs with the ECR to finish this and collect all of that charge that I need to do still. And here are some experimental hurdles I've come up against during this acquisition process. The JN needed a bit of an overhaul here. This is after I've been working on it for a few days, and it's primed and ready to go with a nice, clean-looking hydrogen plasma in the bottle. We also performed an upgrade to our electron cyclotron resonance ion source, and that upgrade actually ended up melting the inner liner of our accelerator. So I had to develop a method to dissipate a lot of RF power that was being dumped into the accelerator. So I built a heat sink for the ion source and mounted that. And right now we're averaging about 800 watts into the ion source. So the ECR ion source has undergone an additional upgrade of just LabVIEW control has been extended out to the ion source. You can actually control the ion source in LabVIEW right in front of it, which is great. Makes things a lot easier. So we have microwave, gas, and this permanent magnet here. This control is out by the source and into the control room. And with the upgrade, we have 3 milliamp at our analyzing magnet, and I have 1.4 at my target right now, which is pretty incredible. So I am poised to start 24/7 acquisition in July. That's all scheduled and ready to go, so I'm going to be very busy very soon. So in conclusion, fluorine-18 is critical to the study of classical nova. Improved oxygen 17P gamma rates are necessary at this point. Direct capture has been shown to dominate the reaction rate, and I think I've made the argument that the LENA facility is ideal for performing this measurement because we have the signal-to-noise boost from the accelerators and from our detection equipment. I'm poised to begin the ECR phase of the experiment, and I'm hoping that improved rates will basically positively benefit classical nova models, explosive hydrogen burning, stellar evolution models, and our understanding of galactic chemical evolution. I'd like to thank all of my professors and all of my peers at LENA. I'd also like to thank the DOE, the NNSA, the Stewardship Science Graduate Fellowship, and CREL. Thank you very much.